quantum mechanics is the only theory of physics for which we don't already know that it's false, or at least limited. We know that, for example, general relativity, which is an unbelievably beautiful theory that describes how the apple falls, how the universe expands, so many different things. We know it's not the final word. It predicts its own demise by predicting singularities inside black holes. We don't know what the Big Bang is, and so on. We know that theory is at some level wrong, right? And that's not a bad thing. Physics has always progressed by having theories that are just better and better approximations. You describe more and more things more and more accurately from fewer ingredients. That's sort of what defines the progress. So it's not normal for a theory to be like quantum mechanics and to have no recognizable flaw.
At the end of our last conversation, you mentioned an interest in talking about the foundations and interpretations of quantum mechanics. And I found that at the time somewhat surprising, just because from other physicists with whom I've spoken, I've gotten the sense that many people working on the cutting edge in string theory or high energy particle physics or holography, they view these discussions of the interpretations as archaic or passé or something like that. So I just wanted to start out by asking why it is that you're interested in the interpretations of quantum mechanics. And maybe for those of our listeners who aren't familiar with what they are, if it's possible to give a brief gloss before we get into some of the details.
Yeah, and maybe I didn't express myself well at the end of our last interview. It's not so much that I like talking about interpretations of quantum mechanics, but I like talking about why I feel there isn't much of a need for them.
Okay.
That I feel that quantum mechanics is a subject that has been treated very differently by scientists from other successful theories, and there's really no theory I can think of that has had such universal success as quantum mechanics. In that many of us seem to feel that there is some kind of problem with it, that it needs our help with something. And my sense is that this comes from a discomfort, a very human discomfort with what the theory is trying to tell us. And I think that's dangerous, because when we want to interpret this discomfort away, we might miss what it's trying to tell us. And to me, that's the most beautiful thing for me about theoretical physics at all, is when we learn that nature is so very different from how we might naively have thought about it. That's the most fun part to me. And it's an insight that's not easily won. You don't just get to make stuff up. You have to think about experiments. You have to think very deeply about how to explain them universally from very simple principles. And then when you've put in that hard work, you come up with a crazy idea that nobody could have really dreamt up, like Einstein coming up with the idea that gravity is just the dynamical shape of space and time, and things trying to go as straight as possible in that curved space-time. That's beautiful, because it tells us something that I think is in a really strong and objective way deeper than the intuitive notions of space and time that we will have grown up with. And that's what makes it exciting, that it's and it's not random. It's not something you just kind of make up and the next day it's gone again. It's true. It explains experiments that cannot be explained in any other way, and that were mysterious before, and gives rise to phenomena that we've since discovered, and so on. So I feel like quantum mechanics is so radical. And I should have said there were all these people that were saying, special relativity can't be true, general relativity can't be true, it conflicts too much with, there's this paradox, there's that paradox. And, this was in the early 20th century, and people went over these paradoxes and they got themselves unconfused about all of them. And of course the theory is true. And once you sort of stop thinking about it deliberately in the wrong way because you're sticking to some, old-fashioned ways of these paradoxes generally come from people insisting on a worldview which is just empirically wrong and trying to reconcile that with what the correct theory is trying to tell them. And that doesn't go well. With quantum mechanics, we seem to have much more difficulty getting to that phase of acceptance and of just letting it tell us how the world works. And, coming around to adapting our own understanding of the world to our most successful description of it.
Right. You said a number of things that have jumped out at me, but one of them is that these discussions that you don't see much of a need for stem as you see it from our discomfort or people's discomfort with what the theory is trying to tell us. And I think that's probably a good place for us to start, especially for those listeners that I mentioned who aren't super familiar with quantum mechanics. So just what is it that you view the bare bones theory of quantum mechanics as trying to tell us about the world?
I would say the most critical difference, or at least the difference between classical and quantum mechanics that tends to lead to the greatest amount of intuitive resistance in very good scientists is all rooted in the principle of linearity or the superposition principle. And this principle is quite easily stated. It says that if you have a quantum state and another quantum state, you get to add these and you'll have another valid quantum state. And in the microscopic world, we have lots of examples of this, and we can verify that it's true without much effort. So for example, we have something called the spin of a particle. Spin of a particle is a little bit like an axis around which it rotates, except that you really should not say that it rotates around an axis, but it's true in the same sense that it tells us that the particle is required to have a certain angular momentum. Like when people make an electron in the electron factory, they can't make any others. They can only make electrons that have a certain angular momentum. The only thing you get to pick about it is which way it points, which in a classical ball rotating would be, what is the axis around which it rotates. So that's the thing you get to pick for an electron. You get to pick that it points up. You get to pick that it points down. And you can arrange for electrons to do that for you. And so I just told you that those are two valid quantum states. Okay, they exist. You can make them in the lab. You can check they're there. Therefore, it's also a valid quantum state to have electron up plus down. That's not two electrons. That's one electron. I'm just putting it in the state of up plus down. If you know anything about vectors, it's like adding two vectors. It is literally that. That's the actual mathematical description of it. So that's also a quantum state. Now, what kind of quantum state is this? What kind of properties does it have? Well, it turns out, and this is something that math tells you, that this quantum state is the same thing as spin pointing to the right. Okay. And how do we know that's true? We know that's true because if we prepare an electron in the state up plus down, and then measure whether its spin is pointing to the right or the left, we will always find that it's pointing to the right. Okay. So this is a principle that's at the very bottom. It's as deeply built into quantum mechanics as anything at all, right? Now here's the problem. So if we think that quantum mechanics is a good description of nature, then it's a description not just of electrons, but also of this chair. Okay. And so therefore, this chair standing here is a good quantum state. Right? But that means that the chair standing here is a good quantum state. I could have put it over there, so that's also a good quantum state. Therefore, the sum of those two things is also a good quantum state. Again, that's not two chairs. It's just a single chair in the state here plus there. Okay. I think a lot of the confusion with quantum mechanics comes from the fact that we never observe that kind of state. We never observe this is called superposition. it's kind of a weird word because it's just another state. Like it's a superposition only if I decided that somehow the more important things to think about is electron pointing up or electron spin pointing down. There's nothing special about up and down, right? Pointing to the right was just as good a description. And from that point of view, it's not a superposition at all. But with the chairs, there seems to be something special about a chair just being here or a chair just being there. And why don't we ever see a chair in both places, right? Or in this weird superposition. And I think it would have been very beneficial to the development of the field and to the I think we would have thought less about interpretations if something called decoherence had caught on earlier, had been discovered sooner. And it's a simple calculation that tells you why you do not see this funny kind of quantum state of chair here plus there. Okay. It's not something that has to do with us conscious observers being here and like observing the chair. It's not important that we're conscious. It's not even it's not important that we're in the room. What's important is that there are particles bouncing off the chair. So even if you just had a single molecule of air in the room, and let's say it was coming down from the ceiling, then, initially the quantum state would be chair here plus there, and this molecule of air. But the molecule will bounce off the here part and not the there part, because it'll miss the chair over there. So in the end, you have some funny quantum state that's basically chair here, molecule moving back up, plus chair there, molecule keeps moving down. Okay. Now, if it is the case that you happen to not know what that molecule is doing, you now have what's called an open quantum system. The chair isn't the whole story. You're missing part of the story because you weren't following that molecule. You can calculate what the description looks like in that picture, and it's something called a probabilistic ensemble. It's no longer chair here plus there. It is some probability of chair here. If I initially weighted them equally, it would be 50%, and it's 50% probability of chair there, and that's a totally different quantum state. It just says that there's a certain chance the chair is here, and there's a certain chance the chair is there, but there's 0% chance it's here plus there. Okay, and again, we can verify that very explicitly with in the microscopic world, where we can prevent things from interacting with an electron. There's really something different about 50% chance that the spin is pointing up and 50% chance it's pointing down versus 100% chance it's pointing to the right. Those are totally different quantum states. And I think this was overlooked for so long because in classical mechanics, physicists are trained to ignore unimportant things, right? When we describe a ball rolling down a plane, to the first approximation, we tend to ignore things like air resistance, right? Let alone what every single air molecule is doing. Forget that completely, right? That's just so not important. And I think this effect called decoherence. So what is decoherence? It's a statement that when we don't keep track of every single stupid little part of a quantum system, then our perfectly good quantum state evolves into a probabilistic ensemble of different possibilities. If you're missing a part of the system, that immediately happens. And there's not just one air molecule in the room, there's like a ton of them, right? So this happens in an instant. This is why we never even see a hint of chair here plus there. We don't follow what these air molecules are doing. We have no idea what they're doing. You'd have to know the exact quantum state of the entire air in the room. And unfortunately, it's not just the room because we'd have to isolate it from the rest of the world. So this happens very quickly. We don't, in the classical regime, we don't expect that this matters, right? I think this is why this was overlooked. I think decoherence, this idea was developed. I'm not a science historian, and I'll have to emphasize that maybe a few times today. So this is really just, but I think it was developed building on ideas that Everett had in the 50s. It was developed in the 70s, 80s. When I studied physics as an undergrad in the 90s, nobody taught this. It requires you to understand that there really is something quite dramatically different about the quantum world, which is that interactions, with systems matter, even if they don't move the chair, even if they don't scratch the chair, even if they don't do anything that classically we would have cared about, they carry away quantum information. They get what we now call, the environment gets entangled with the system. And the difference between the macroscopic and the microscopic world isn't anything fundamental. There's no line that you can draw between what's small and what's big and what quantum mechanics applies or doesn't apply. It's a practical issue. You can easily isolate small systems like electrons from the rest of the world, but you can, in practice, not at all isolate a chair. Even if you took all the air out of the room, it would still radiate photons because it's warm. You'd have to cool it to 0 temperature and so on. So it's just an absolutely hopeless idea. And so this idea of classical reality, people struggled with this idea. Where does classical reality come from? It's an emergent concept. It's not a precise, infinitely precise concept. It's like resistance in a conductor or insulator or something. It's a concept that emerges when you're dealing with very large objects, which are in practice impossible to insulate from an environment. So I didn't learn until I was I think a postdoc. That's the first time I heard about decoherence. It's super embarrassing. And I was so furious that this wasn't taught to me and that people would go on and on about the measurement problem and the conscious observers and whether that's important or not. And I still can't believe that the person who taught me this was Nima Arkani Hamed, who's obviously a great scientist, but somehow that just gives you an idea of his breadth, I guess. He was like, "Oh, why are you worried about this stuff? There's decoherence." And immediately, so many things made sense. I'm not saying that, we understand everything as deeply as we'd like to, but there are so many confusions about quantum mechanics that just don't make any sense when you ignore the fact, or they're built on ignoring the fact that large systems interact with an environment. And you can't ignore that. You can calculate what happens as a consequence, and what happens is just inconsistent with these confusions. Right? So for example, the issue of when you make a measurement, what actually makes the outcome somehow definite. At some level, you're just correlating an apparatus with your quantum system. Like if I measure whether the electron was pointing up or down, the spin was pointing up or down, I could say quantum mechanics just tells me that now I have a new quantum state in which I have apparatus needle up, electron up, plus apparatus needle down, electron down. Sure. But the apparatus needle is like this chair. It can't be in a superposition of up plus down for very long because it's going to interact with an environment. And now we understand why measurements have definite outcomes. They have definite outcomes for the same reason that in practice, we will always see the chair either here or there and never in a superposition. For the same reason, we don't see apparatus needle plus up plus down. It's the very fact that I've sort of coupled the system, the tiny system, to a large apparatus that has now made it impossible for it to stay what's called coherent, to stay in this funny superposition type state.
You mentioned Nima Arkani Hamed. Was this when you were both at Stanford?
No, this was certainly this discussion happened at Harvard, and I can't pinpoint the exact year. There was one year I did spend at Harvard. I don't know if it was that year or if it was maybe earlier when I was just visiting. He was a faculty member at Harvard for a little while as well. So I don't, but it was in the early 2000s.
Okay. You did your postdoc at Stanford though, right?
I did do a postdoc at Stanford,
okay. Yeah. Well, speaking of Stanford and decoherence, I would like to get back to decoherence when we talk about your joint work with Leonard Susskind, because decoherence will become important then. But before then, and I will again emphasize that you are not a science historian, so I am not going to grill you on all of the various interpretations and theories, but I do have a question about this distinction between interpretations and theories. People use the word interpretations of quantum mechanics a bit differently, I've gathered from some of the conversations that I've had. And many of them have been with philosophers. And many philosophers, some of whose work might come up in this conversation, I don't know, have pointed out that these might not be, or they aren't different interpretations of one theory. I mean, Bohmian mechanics versus GRW, these are different theories that make different predictions. So I just wanted to ask you what it is that you're referring to when you say the interpretations of quantum mechanics.
Yeah, I'm not aware of any successful modifications of quantum mechanics. And so to the extent that there are different theories, I'd be quite interested in learning more about them. To my knowledge, it's very difficult to change anything about quantum mechanics in a way that doesn't immediately make it either not self-consistent, like mathematically inconsistent, or inconsistent with observation. I suspect that that's a pretty controversial statement, but I think that I'm aware of, I've certainly heard a lot of talks by people who've been trying to sort of get back to a more, what they consider, I think, again, based on a subjective bias, a more objective reality. Like maybe this decoherence somehow happens automatically all the time due to, I don't know, quantum gravity, some coupling. So if you want that to happen, then you have to couple your system to some other system that we don't observe, that sort of that plays the role of the environment. Like if you don't want this to be an emergent phenomenon that happens because of practical reasons, we can keep track of the molecules in the room. That makes it an emergent phenomenon. It's not a fundamental thing. I think a lot of people are trying to come up with ideas where it becomes a fundamental thing, and the wave function collapses, and it's really objective, and everybody will agree that this happened, no matter how much information they have about the world. That's very problematic. It's a bit like introducing an ether or something like that. You're clinging to your old ideas, and it forces you to introduce things that you can never actually observe and have them do the work for you. So I really struggle with the idea of what it even means to. Yeah, what does this mean to interpret a physical theory? I think what we should ask is, what does the theory tell us? What consequences does it have? And we should seek out the ones that make us the most uncomfortable. We should sharpen those. We should, push as hard as we can on the sore spots, and see, where do we land? Do we land on an actual self-inconsistency of the theory, some kind of self-contradictory statement that's mathematically impossible, logically impossible? Do we land on a conflict with observation? Oh, maybe, I don't know, quantum mechanics is in conflict with special relativity and allows things to go faster than the speed of light. Turns out it doesn't. Or do we land on, wow, this thing hangs together completely, it's self-consistent, it's consistent with observation, and the world is just so wild, and isn't that fun? And let's just take it all in. And I feel like with quantum mechanics, we're clearly there. That's where quantum mechanics is. It's almost, I once wrote a contribution to some book about the unreasonable fact that quantum mechanics is the only theory of physics for which we don't already know that it's false, or at least limited. We know that, for example, general relativity, which is an unbelievably beautiful theory that describes how the apple falls, how the universe expands, so many different things. We know it's not the final word. It predicts its own demise by predicting singularities inside black holes. We don't know what the Big Bang is, and so on. The theory is clear, and also it just doesn't involve quantum mechanics, and we know the world is quantum, so we know that theory is at some level wrong, right? And that's not a bad thing. Physics has always progressed by having theories that are just better and better approximations. describe more and more things more and more accurately from fewer ingredients. That's sort of what defines the progress. So it's not normal for a theory to be like quantum mechanics and to have no recognizable flaw. That's not that I mean to say that we know for sure that it's going to be part of whatever the complete description of all phenomena is, some unified quantum gravity theory. I don't know that. But unlike with gravity, where I know the classical theory is definitely not going to survive at that level, with quantum mechanics, it's entirely possible it'll survive. It's in my view, completely self-consistent, and it just has elements in it that make us, that are a little bit hard to swallow. But I don't think they're qualitatively that much harder to swallow than telling you that, you can't accelerate beyond the speed of light or that space and time are curved. It's just not, it's not how we grew up.
Your reference to these sore spots that aren't there, I find very interesting. Naturally, many of the philosophers I've spoken to view, for instance, the wave function and wave function collapse as a potential sore spot, because some people, namely spontaneous collapse theorists, think that the wave function collapses. Others might think it just branches. But we'll set that aside. For now, two other sore spots, though, that I would think might come to mind, maybe you don't view them in this way, stem from quantum field theory, which I imagine is what you are referring to when you say it's like the most successful theory we have. And the two that I have in mind are dealing with all of these problematic infinities with plausibly ad hoc technical tricks like renormalization. That's one thing that some people, I think, find problematic. And then the other, which you alluded to, is quantum gravity, but maybe that's not so much a sore spot for you with quantum mechanics as it is just a problem with general relativity. But those are two potential sore spots I'm curious to hear about.
I meant neither of them. And I'm glad you asked, because I think I didn't express myself very clearly. So I think it's important to distinguish between quantum mechanics as a sort of basic framework and its many applications. Okay. So what I would think of as quantum mechanics is effectively a theory of information. It's really about how information is distributed, what it means to know something, and what it means to communicate something. And this is a very bare bones framework. It says that states are, you can literally, the first thing I tell students in a quantum mechanics class is, states are vectors in Hilbert space. It's a mathematical thing. Observables are Hermitian operators. Doesn't matter right now what these things are, but there's like a set of things you say, and then you put them together, and here's your theory. And this doesn't say anything about whether the world has electrons in it, or photons, or quarks, or maybe strings, maybe not, I don't know. It's just a very basic framework. And now here's how you calculate probabilities. Here's what happens when you forget about part of your system, and suddenly you have to talk about probabilities. So that framework, for example, doesn't suffer from the kind of infinities that we might have to worry about in quantum field theory. Those infinities have to do with something that has very little to do with quantum mechanics. It has to do with the fact that quantum field theories are generally effective field theories, meaning that they're intended to describe the world at certain distance and energy scales and not at higher energies than that and shorter distances than that. If it were necessary to know how the universe works all the way down to the shortest distances, then we would have never made any progress, right? We still don't know that. So but we come down with our effective descriptions where at a certain energy it makes sense to talk about electrons. It makes sense to talk about photons. It makes sense to talk about atoms, for example, but maybe at much higher energies it doesn't make sense anymore because the atoms will be blown apart and you have to discuss nuclei and electrons. Even higher energies, you talk about individual parts of the nuclei like neutrons, protons, maybe quarks, and so on. That's a story of phenomenology. It's a bit like it's an inventory, and you don't know the inventory all the way down to the short distance scales, and that causes some problems. But I don't think that has anything to do with deep problems about quantum mechanics. mechanics. Quantum gravity is an incredibly deep problem, about which I think we talked a fair bit last time. And you know, I'm definitely very open to the possibility that when we discover the right theory of quantum gravity, that it might involve some modification of quantum mechanics and not just of general relativity. I remember being sort of irritated as even in high school when I heard about people wanting to quantize gravity all the time. I had literally no idea what I was talking about, but it felt like, wait, why are they so, how do they know that something's wrong with gravity and not with quantum mechanics? Like, why are they already picking a winner? You know, like maybe, and part of me still feels like that would be kind of cool if we discover, you know, something that also tells us that quantum mechanics is just an approximation to something else. But again, I think it's remarkable that we can't be sure about that. That's quite interesting, and so I think one has to have an open mind. Maybe it'll survive, maybe not. I think by sore spot, I mean more like the kind of thought experiments along the lines of what people were struggling with in the early days of quantum mechanics. Schrödinger's cat, that kind of thing. That was a beautiful thought experiment. You know, like you have a sort of superposition of atom is decayed and atom is not decayed. And if you had the atom in complete isolation, you could maintain that superposition, but you have a Geiger counter there, and the Geiger counter is going to count when the atom has decayed. That's coupling the system to a macroscopic, the small system to a big system. And at that point, from our modern point of view, we would say decoherence happens. The environment bounces off this Geiger counter. It'll know if a click happened or not. That affects how air molecules move. And in an instant, if you aren't keeping track of all the air molecules and all the photons and everything in the world, you will no longer have a superposition of atom decayed and undecayed. You'll just have certain probabilities for both possibilities. And so then when you bring the cat into the picture, in the Schrödinger's cat experiment, the decay of the atom is supposed to trigger the death of the cat by some obscure mechanism. If people had known about decoherence, the cat wouldn't have added anything interesting to this picture. The cat is just part of this microscopic world. It will immediately decohere. It'll either be dead or alive. Whether or not I open the box and look at the cat is completely irrelevant. But people got themselves tangled up in knots over how important it is that a conscious observer opens the box and sees if the cat is alive or dead. So I feel like that was a good thought experiment. And that was what I mean by a sore spot. But it's, we really did surprisingly poorly. Normally when you discover a new theory, like Einstein discovered special relativity, Einstein discovered general relativity, the first thing you do is you understand how to recover what, your previous description of nature in the regime where that was valid. So just, Newtonian space-time, Newtonian gravity. That was a great theory, explained to pretty good approximation how the planets move and how the apple falls. So you got to be able to get that back out. That's why we don't just get to make random stuff up. It has to be consistent. And people had no trouble, deriving this. It's just a bunch of formula. You just, take the right approximation. Things aren't, too massive or too fast moving, and out comes your old theory plus tiny, tiny corrections that you say, yeah, of course, yeah, we haven't ever measured anything precisely enough to see that. So everything makes sense. With quantum mechanics, we totally failed to do that. We totally failed to understand how what we perceive as reality in the sort of classical world emerges from this new theory. And I think the sort of wrong turn that was taken in response to this Schrödinger cat type thought experiment is a good illustration of that. We got tangled up with like the meaning of consciousness instead of just doing a calculation. The calculation in this case is what happens when your closed quantum system becomes an open quantum system, when there are parts of the world that have interacted with your system that you're not keeping track of. And underestimating how important that is, how important even the interaction of a single elementary particle with your system can be for its description. And I think today even now that we understand decoherence, I guess I have a favorite sort of litmus test for like how much pain can you tolerate. That goes like this. So it's basically, I was later told a version of something called Wigner's friend. But I like to think of it in terms of a spider that has surrounded the galaxy with an impenetrable spider web.
Okay.
Don't ask. Don't ask.
It makes me think of holography.
Yeah, but gravity is not going to be important for this story. So, but you're right. We could bring that into. But the point is just the following. The galaxy is very big. So it's 100,000 light years across or something. So it takes 100,000 years for anything to even get, like if I shine a flashlight into empty space out there at night, it's going to take 100,000 years for those light particles to leave the galaxy. Okay. And similarly, if I do a Schrödinger's cat experiment here, it's going to take 100,000 years for whatever the particles are that got entangled with the cat to leave the galaxy. Okay. But let's go back to sort of minimalist version of this experiment where, I have the chair here plus there, and there's just one particle that bounced off it or not. It was coming down towards this version of the chair, so it bounces off this version, but it doesn't bounce off that half of my wave function or state. And so if I forget about the particle, I get to this probabilistic distribution of like chair here, 50% chance, chair there, 50% chance, chair here plus there, 0% chance. I break up the coherent superposition. Okay. Now, in that story, if it's just one particle that did it, I could imagine changing the story. I could imagine saying, hey, I could catch up with this particle. How about I bring another reflector somewhere that just reverses this whole effect and makes the particle go back up to the ceiling. And now I've restored the superposition of chair here plus there, and the particle is again just up at the ceiling. I've undone this interaction. It's very easy, right? If I have a particle, just one particle that moved from here to there, I can very easily make it go back again, right? What's hard to do is if there's all the particles in the atmosphere of this room that have bounced off the chair, there's no way I can try to undo this and revert to the original state. And so this is exactly, this is why we say it's an emergent phenomenon. There's nothing truly fundamental about it. It's just a practical issue, right? Now, what I just told you is actually not because of me, but it's very profound, right? It tells you that this idea that we've measured where the chair is and that the chair has gone from being in a superposition of here plus there to like being either here or there, that's not 100% objective. It's not like something that's, unchangeable. In the example with one particle, I could easily revert it or simply keep track of the particle all along and just have a superposition of chairs and particles. It's only when I forget the particle that the definite outcome will be there in some sense. And now I could add another particle and another and another, and clearly it gets more and more difficult to keep track of them all or to catch them and make them go back to where they started out. But it's a sliding scale. It's not like, there's no, when I add the 17th particle, now it's completely irreversible. No, it's just it got a little bit harder again. And when I have the whole atmosphere, well, it just got insanely hard because there's like 10 to the 23 particles here. And so it's like exponentially hard. So why did I revisit this? Well, now I want you to think of the spider that has surrounded the galaxy. And in that spider's viewpoint, the whole galaxy is just one big quantum system. And it absolutely includes all the particles that have bounced off the dead and alive cat and that have made it either dead or alive from our point of view, because we haven't kept track of those particles. The spider says, oh, I have a quantum state. I can think of it in terms of decomposing it into a history where there's a dead cat and everybody's crying, and there's an alive cat and everybody's happy. And that's one way I can choose to break up the state. It's sort of like when you have a vector that points this way, you can choose to say it's the sum of these two vectors. You choose a basis. To us, this basis is very fundamental because it's sort of picked out by the locality of interactions, the fact that things interact with each other at specific places. That's why air molecules bounce off a cat. But for the spider, this is all the same. It's just one big thing where nothing has really happened. And that's like, I would say that's definitely a sore spot. You have to acknowledge that the theory tells you that the description of the world by a super observer who has somehow isolated the whole galaxy and has an understanding of its whole quantum state is totally different and seemingly naively in contradiction with the description of the world by people in the galaxy who are subsystems of the galaxy, don't keep track of everything that's going on, who will say this happened or that happened. And so now your job is to take this and see if you can arrive at an actual contradiction rather than just a discomfort. People were going crazy over the fact that there's length contraction in special relativity, and some observers will say the car is shorter when it's going faster, and so on. And that turns out to just not be any contradiction at all. As far as I know, this doesn't either, but a lot of people I know are extremely uncomfortable with it. I kind of embrace it. I love the fact that that the world is crazy enough to do this. So, for example, you could ask, can the spider and us argue about this? And the answer is no. The spider would have to make a hole in the spider web, and in order to talk to us at that point, basically information will escape from the galaxy. We share a common environment. This is why we all agree on what happened. You could also ask, why don't some of us end up thinking the cat died and some of us end up thinking the cat's alive? It's a calculation. You can just calculate that there is a probability for the cat dying and everybody being sad and there being an obituary in the newspaper and all of those correlated things that happen when the cat dies. And there is a probability for the cat is alive and everybody's celebrating and next year it has kittens. And there is, and you can calculate it, zero probability or really unbelievably exponentially small probability for cat died, everybody's celebrating. It's a calculation. It's not something we just make up. And so it explains something. But this calculation is based on the fact that we all share what I call an environment. By environment, I mean the stuff we don't follow, the stuff we don't know about. It's not important exactly what that stuff is, just that there's enough of it and that it's all interacted with the systems we care about. This is because there is such an abundance, an overabundance of things we don't know at the sort of quantum level. Quantum information is somehow very precise and delicate, and we know almost none of it. This is why it's so hard to build a quantum computer. Even when you try, it's really hard to hold it together. The spider knows, in my fantasy, knows all of it. Of course, totally impractical. You can't build such a good spider web. The galaxy would radiate. Like, how would you even insulate it that well? In practice, not really possible. But we can imagine, slowly extrapolating out to that situation from lab setups where we can arrange this sort of thing. Just put more and more in the lab until you have conscious objects in the lab that do experiments on each other and have cats and so on. And it's just what the theory tells us. The theory tells us we're going to have a specific history with some probability this will happen, with some probability that will happen. And for the spider, it's all just one sum, and it never breaks up into pieces. I'm very comfortable with that. But I think it's a sort of, yeah, I think a lot of the struggles people get themselves into with interpreting quantum mechanics, modifying quantum mechanics, and so on, are based on sore spots like that they somehow cannot tolerate.
All of that was incredibly fascinating. But one of the things that I most want to jump on and ask more about came at the beginning, though you've referenced emergence a number of times since then and contrasted it with fundamentality. I think I'll add another word, which is effective. So general relativity, you don't think is the fundamentally correct theory about the world, but it is a highly successful, effective theory in a certain regime. You've voiced a lot of confidence that the world is fundamentally quantum mechanical, even if you're open to the possibility of revising that quantum mechanical framework in the future at some point. And what I wanted to ask then is something like string theory, which I take it is fundamentally quantum mechanical. You accepted that quantum field theory might have some issues perhaps with the infinities that aren't ideal.
There's a question of what physicists call the UV completion of a theory. So when you try to describe nature at a certain scale, the scale is part of the theory. That's I think how we've learned to think of quantum field theory. And it's not meant to make sense. The same theory is not meant to make sense at a different scale. So when you naively extrapolate it to much higher energy scales or shorter distance scales, it might, give you nonsense answers, and that's totally okay. What tends to happen is that on your way to these higher energies, you discover that there are some new elementary particles, for example, that you didn't know about before. And that the things that you were thinking of as sort of your fundamental ingredients at a lower energy scale, like, I don't know, a nucleus, are really made up out of, smaller ingredients that have their own little laws of nature that you now need to actually put in order to describe them well. And so, your naive extrapolation to high energies was just wrong, that you were missing some new phenomena that happen along the way. That just strikes me as a totally harmless situation. I mean, it's not surprising in the slightest. In hindsight, it's not surprising that if you made such a naive extrapolation, you might have gotten nonsense answers. One of the possible things that might happen as you're going to very, very, very high energies is that your particles are all really made out of strings, deep branes and things like that. That's an example of a UV completion of the theory. By UV, it's a funny technical term. It refers to ultraviolet, and it just refers to the fact that ultraviolet is like the light is smaller wavelength. It's a smaller thing than infrared, which is long wavelength. So this terminology has gotten a hold in physics where we talk about the ultraviolet completion, meaning just when you go to ridiculously small scales compared to what you're working at, something new needs to come in. And that's fine.
The question that I wanted to ask, though, goes back to this distinction that you drew between quantum mechanics and quantum field theory. And string theory, I understand, is fundamentally quantum mechanical. Then on the other hand, we have quantum field theory, which is also quantum mechanical, but it is fundamentally a theory of fields. And my question is just whether you're much more committed to there in the end being a fundamental quantum, the final theory of everything will be a quantum theory, but not necessarily a quantum field theory, even though quantum field theory is what is currently regarded as this uber successful. It undergirds the standard model.
I'm sure it won't be a quantum field theory in the sense that we use it today, like to describe. So there's actually a quantum field theory that is a complete quantum gravity description of a certain class of spacetimes. Right? There's this famous ADS-CFD correspondence, right? But in that case, the quantum field theory lives on the boundary of the spacetime. It is UV complete. There are no infinities. You can work with it at arbitrary energy scales. It's a very special kind of quantum field theory. And it sort of holographically describes what's happening inside the space-time, and it describes all of gravity and so on. So what I'm sure will not be the case is that quantum field theory is valid fundamentally inside the space-time. We know that that's in conflict, for example, with the holographic principle. We know that it has way too many degrees of freedom, way too many different sort of things you can excite compared to what gravity will actually allow you to do. But I want to come back to what you said in the beginning, just to sort of make sure I didn't come across as completely certain that quantum mechanics will be part of the final description of whatever unified theory of nature, of everything. What I wanted to stress is how remarkable it is that we don't know that it won't be part of that description. Again, for gravity, we already know that general relativity, the best theory we have right now, will not be part of that description. It'll not be sort of true at the most fundamental level. With quantum mechanics, we have no idea. And that's really surprising. You would have thought that by now we would have discovered some kind of flaw with the theory that would tell us that, we better fix that one up too on our way to a theory of everything. But I don't want to claim that I have a particularly strong, I would assign strong probabilities to whether or not quantum mechanics is going to end up getting modified. It is quite remarkable that there's at least one example where you have complete quantum gravity theory, at least for a certain class of spacetimes, unfortunately not our world, which is 100% quantum mechanical. That's an interesting data point from which you can extrapolate any way you like. I don't know if I wouldn't regard it as conclusive.
I don't want to dwell on the holography stuff just yet. Maybe if we have some time at the end, we can return to it. But I do have one quick question about something you just said, which is that you're very confident that the bulk will not be fundamentally quantum field theoretical. And what I'm wondering is if this is just a belief that is very common in string M holographic M theory, holographic centered physicists, or if this is really just a very common view among physicists that the world will not be fundamentally quantum field theoretical.
I don't think I should be speculating about how common it is, but
okay.
I can.
This is more of a sociological
yeah,
question.
Exactly.
I'm curious.
You talk to a lot of people, so you're probably better positioned on I mean, the kind of people I mostly hang out with, I don't think this would be a controversial position, but that's there's an echo chamber risk here. So I just say that there are scientific reasons why we think that quantum field theory is at best a highly redundant description, and they have to do with gravity. They have to do with the fact that quantum field theory is a local theory, meaning that you can sort of independently in different parts of this room excite degrees of freedom. You can change things around as you like. And if you try, so that would make you think that you can store a certain amount of information in this room, let's say as many bits as there are air molecules, by just arranging the air molecules in a particular way. But maybe we could store more information by breaking up the air molecules into smaller pieces, and just depending on how small these pieces are, let's imagine a little tiny cube of volume, then it's how many cubes of tiny little volume fit into this room, right? That would measure how much information we can store in it, and that turns out to be false. So the maximum amount of information you can store in this room does not ultimately grow with how many tiny cubes of volume. To just find the smallest thing you can make, and then store your information in that stuff. Maybe it's strings. That stops working at a certain point, because it turns out that that making all these small things cost you a lot of energy, and energy is like mass, it gravitates, and if you have too much energy in the room, it's going to make a black hole. And at that point, you can't add more information without making the thing bigger. Right now, I was limiting myself to this room. So this is sort of the very basic idea of the holographic principle, and it has a priori nothing to do with string theory. It's just an observation about how gravity interacts with information, given very basic ingredients about how we know information can be made and stored. And it imposes a limit on the amount of information that turns out to be proportional to the area of the walls of the room. It's quite a surprising statement, given that we started out with a local theory in which you would think that the information grows extensively with the volume. So it grows at a higher rate. Let's say if we double each dimension of the room, it should, the maximum information content should get multiplied by 8, but actually it only gets multiplied by 4 because the area only scales like the square of each length. So that's why, I think this is a very robust argument. It's not incredibly precise the way that I gave it, but it's been made more precise, including through my own work, that connects areas to the information, areas of surfaces to the information content of adjacent space-time regions. And this tells us that quantum field theory doesn't correctly capture how much information there is around in the world. It has way too many degrees of freedom. It includes a lot of things that, could happen, which can't actually all happen simultaneously. If you look at a typical quantum state of a quantum field theory that you construct abstractly, and then add in gravity, you'll realize the state was completely inconsistent because there's way too much energy in it, and the space-time on which you thought this state was existing or living is actually not consistent with general relativity, which tells you that it should have all been curled up into a really big black hole or something. So that's why my level of confidence in quantum field theory as a sort of truly fundamental description of nature in the bulk, as you correctly put it, is low.
Okay. Yeah, I could talk about holography all day. Actually, I find it incredibly fascinating. But I have teased, well, I didn't actually tease Lenny Susskind, but I've teased the name to our listeners. And just the other day, last night, I read through a paper that the two of you co-authored. And you are both, though Lenny perhaps a little bit more well-known for having some crazy out there ideas and very fascinating work. And cosmology isn't something that is often brought to bear on these discussions of the foundations of quantum mechanics. So first, toward getting at this comparison between the multiverse and the many worlds theory, just what is the multiverse and what is the motivation behind it, whether from a string theoretic or cosmological perspective?
Yeah, that was a really fun paper. Lenny is, of course, one of my biggest inspirations. He was one of the people who really came up with together with 't Hooft, with this idea of the holographic principle, and inspired my own work on that. And he's also somebody who is never shied away from, in physics, it's very tempting to work on parts of a subject, parts of a problem where you know exactly what to calculate and you know how to calculate it, and you have all the tools that you really wish you had available. And so what you get from your work has the value of being mathematically rigorous. It is going to be mathematically correct. But there are obviously some limitations. So for example, we're very good at describing certain kinds of universes from the outside. ADS-CFT is an example of that. It's one of the greatest triumphs in physics of all time. It's a complete quantum gravity theory for, unfortunately, the slightly wrong universe, but still, it's an amazing accomplishment. You can ask so many important questions about what happens when you make a black hole and it evaporates and so on. But one of the important limitations, and people are grappling with that, of course, is that you're treating the universe like an object in your lab. It's as if you were on the outside, you send stuff in, stuff comes back out. That's sort of what this conformal field theory, the CFT that I mentioned earlier, really describes. And here we are in the real world on the inside looking out, right? We're not in control of any universe. We're in the middle of it, and we're a tiny, tiny part of it. And when you start, trying to connect what we know how to do well in physics, especially in quantum physics, to that perspective, which unfortunately is the actual situation we're in, that turns out to be really hard. And you lose all that wonderful control and all that wonderful precision, and you don't even know exactly what you're supposed to calculate. Another example is supersymmetry. It's wonderful to have a certain symmetry in your calculations, and it gives you so much more power, but it's not in the real world. What do? Do we just never talk about the real world anymore? So, of course, we do both, right? We do rigorous stuff where we can calculate exactly, and we maybe take some lessons away from that. But we mustn't forget to go back to the real world, which is messy and hard to think about in an infinitely precise way, and we don't even know what to calculate. You've got to be able to leave that pristine regime and remember what you're here to do, which is to explain the real world. And Lenny's always been, he's never shied away from that. And I think the paper we wrote together is an example of an attempt to do that. And I think it also maybe benefits from a reader who appreciates that this is not done in the same pristine environment as some other papers that get written, including by Lenny or by me. And so there's a degree of speculation involved, and that's probably putting it mildly. But I think what we do in that paper is to point at some of the deep questions that arise when you try to do quantum mechanics and cosmology. Maybe I should have said that at the beginning. To the extent that I think there's still a mystique that should be legitimately attached to quantum mechanics, where we, don't quite understand what it means and how to apply it. It's when we talk about the universe as a whole. I don't know if there's much more to it than the observation that when you try to talk about the universe as a whole, well, you can never talk about it as a complete quantum system in practice, because you will never have access to all of it. You're a part of it. Think of quantum mechanics as organizing information that you have. And so maybe, you can't measure it, right? So the way we prepare a quantum state is, in effect, is usually by measuring a quantum system. Now we know it's in that state, whatever we found. We can't do that with the universe. There's certain things you can't do. And so I think most of the important problems with how to, think about quantum mechanics have to do with the situation where you're trying to apply it to cosmology or to the universe as a whole. And that's what we try to do. And we try to kind of do two different things. The thing that was, I guess maybe where I was maybe a little more of the driving force was one thing, and then the other one, Lenny was maybe a little more of the driving force, but I think we were both comfortable enough with each that we were happy to just put it all in one paper. The thing that I was excited about at the time was that we had been struggling with certain infinities that very easily arise in cosmology. The universe, when you describe it globally, tends to want to get very big and just keep on growing forever and ever and ever, and then you can get confused about what thing is more likely than what other thing according to your theory, because all of those things happen infinitely many times. And then how do you decide whether a theory is right or wrong? This is called a measure problem in cosmology. As such, it doesn't really have too much to do with a multiverse. The multiverse is a very special situation in which the measure problem arises, in which the number of possible versions of the world or low energy physics type arrangements of particles and forces is very large. But you don't need that to have to worry about the measure problem. The measure problem is a much more robust situation that we're almost certainly in.
Could you explain why we're certainly in this, most certainly in this, even
yeah,
if we're not?
I can. It has to do with the fact that in order to get this problem of infinities in cosmology, all you need is a phase of accelerated expansion that is sufficiently stable locally. So right now, we're observing that the universe is in fact undergoing accelerated expansion at a rate that's consistent with a constant driving force called a cosmological constant for that expansion. And it would require a sort of real fine-tuning or a sort of conspiracy for that phase of expansion to suddenly abruptly end in the next couple billion years. It's already been going on for a couple billion years. If sort of the decay rate for that driving cosmological constant was only millions of years, then it should have already been over. And if it is 100 billion years, well, that's already enough that globally this expansion will continue forever and ever and ever, because what will happen is that the cosmological constant will decay to a lower value and the acceleration will stop, but only in a part of space. And that part of space will grow and grow and grow, but it can't catch up with the even faster growing accelerated expansion going on around it. So there's a sort of, there's a critical value. The cosmological constant that's driving the accelerated expansion would have to decay faster than a certain critical value of 10 or 20 billion years, or else it goes on forever. And at this point, having seen that it's already lasted for something of 7 billion years, means you would really you would need to somebody had to dial something to make it decay in the next 10. So it's very natural, to say the least, that just what we have observed about the own phase of the universe in which we are living right now. And so I'm not speculating about inflation, eternal inflation in the sense that it's usually discussed. I'm just basing this argument on what we are seeing the universe around us is doing. You'd have to fine-tune to get an explanation of what the universe is doing right now without also getting this eternal expansion that then leads to this infinities problem, this measure problem. So that's why I claim it's a very robust problem. You can get it without positing that there's a whole multiverse. I mean, there's reasons why we posit this. This is an idea that Joe Polchinski and I had, but it's
a really exciting idea.
You can be very skeptical of our idea about the multiverse, and you would still need to worry about the measure problem. It's a very robust problem in physics. And what I was bothered by, there was one thing I was bothered by, and there was one thing that I was excited by that both sort of led me to this paper. What I was bothered by is that when we describe the trouble that gets us to these infinities, we're really describing the universe in a way that's not self-consistent. We're acting as though, you see, when this vacuum decays, when this cosmological constant decays and becomes a smaller one, as I was just describing, what I was saying is, well, that'll happen in one place, and then a bubble will form of this new vacuum, this new kind of state where it's not expanding so fast anymore. This bubble will grow. That's like radioactive decay. It's almost exactly the same type of phenomenon. And when you're describing the universe as a whole, you shouldn't say that it happened. Like, which environment did you pick here? Which degrees of freedom in the universe did you choose to ignore in your description to make this bubble form at one particular place? It could have formed over there. It could have formed later. It could have done a lot of things. What's really happening is that the universe is evolving into a state where there's a superposition of bubbles that with greater and greater amplitude are sort of situated at different places. And that means it's evolving into a state which really has no good semi-classical description at all, because the shape of space-time is totally different inside these bubbles and outside. So we don't know how to describe this kind of universe. So there was something just wrong about, what's true is, like, if one of these bubbles forms next to you, and if it wasn't as deadly as it really is, you would see it forming in the same way that you see, the Geiger counter clicking, or hear the Geiger counter clicking. Yeah, sure. But that's because you are a limited observer who doesn't observe everything, who has an environment, and that takes away quantum information. And so to you, there's a specific history. But we're trying to describe the whole universe here, which is the you that we're picking here. I don't know how that works. So that bothered me. Like the whole sort of infinities picture was kind of it was built on an inconsistent theory. And at the same time, we had learned from ideas about how quantum black hole physics might work, based in part again on Lenny's idea of complementarity. Lenny and John Preskill and others had this idea that it might be necessary to restrict to one observer at a time, that physics doesn't necessarily have to give you answers that are consistent between two observers if the laws of physics themselves prevent these observers from comparing notes. So for example, an observer who fell into a black hole and an observer who stayed outside might not be able to compare notes. And so then naively, you might think there's a contradiction between what I said is going to happen to these observers, but since they can't compare notes, it might be okay. So this is a very brief sketch of the kind of ideas that were floating around, but the upshot was, it's often important to not ask questions in physics about where a violation of the laws of physics is already built into the question. So maybe we shouldn't ask about what two observers will argue about if they can never argue because of the laws of physics. Okay, so then maybe how do you generalize that into some kind of more general principle? Well, maybe we should always just talk about what is in the causally connected history of one observer. It doesn't matter which observer, you have to be able to describe any observer, but don't try to simultaneously describe people that can't ever talk to each other, right? And so I was taking this very seriously, and it seemed natural to me to try to apply this to cosmology. If it's important for black holes, then it's probably important to cosmology. And I built a whole research program around trying to get rid of these infinities by restricting to what one observer can see, which turns out to be much, much, much less than this infinitely large universe. Okay. And later we realized that there's actually a kind of mathematical correspondence between what one observer can see, which is, I think, a much better motivated sort of thing to think about and compute probabilities with, and this fictitious infinitely large universe in which we kind of pretend that, I don't know, unknown observers are measuring where these bubbles are forming. I still think that the sort of local description is, in some sense, the more fundamental one, but you can recover the global one by kind of putting together all the things that could happen to one observer. It's just like with a radioactive decay chain or something. Well, it could decay to this other element and then to that one, or it could have happened in some other way, right? You put these things back together with their respective probabilities and just present them as one big multiverse or very large universe in which all these different possible outcomes actually happen at different places. And that's what we meant by, comparing the many worlds, the many different decay chains that one observer might have seen. They'll only see one in practice, but it could have been others, right? To the multiverse, to like what's actually represented in different causally disconnected parts of the space-time. That was one theme, and the other theme had to do with what if we want quantum mechanical amplitudes, quantum mechanical probabilities to be something precise and rigorous? Does this idea of, and for this you kind of need something like the multiverse that Joe and I proposed, or a string theory landscape.
Could you explain where that comes from for our?
Oh, that's a long story. I mean, it came from the fact that we have a very small cosmological constant in our universe. So the cosmological constant is the energy density of the vacuum. You might find it funny that the vacuum has energy, but it does. And in fact, what's funny is not that it has energy, but that it has so little. Why is that funny? Because we have great theories that are otherwise well tested and work super well, like the standard model of particle physics, which tell us that there are many contributions to the energy density of empty space, all of which are like 50, 60 orders of magnitude larger, at least. And that's just based on which part of the theory we're confident about. than the observed value. So you have to explain why all these contributions cancel to such a ridiculous precision, and moreover, why they cancel to this precision now, as opposed to, for example, in the early universe, where those contributions would have been completely different. Because, say, electroweak symmetry breaking wouldn't have happened. That would change the equations completely. And so the cosmological constant must have actually been quite large in the early universe. What's going on? What is making this happen? And it's not a symmetry, because if it were a symmetry, then that symmetry should be glaringly obvious to us. The energy scale that's associated with the value of the cosmological constant is extremely low. It's not something that we haven't built strong accelerators yet to sort of explore. It's like you can. It's a nothing energy scale. It's a joke. We know there's no symmetry. So the proposal that had been sort of floating around for a while, due to Weinberg and many other people were thinking about it, is maybe the cosmological constant is a kind of random variable that can take any value, and maybe it's like different branches of the wave function have different values of the cosmological constant. Maybe different parts of the universe have different values. I don't know. There weren't any good models for it that didn't run into other problems like producing an empty universe. But the basic idea was that perhaps the smallness of the cosmological constant has to be explained by a combination of finding a theory where it can take on many different values with an anthropic argument, saying, well, now what selects for the presence of a small cosmological constant is the fact that observers can't live in places with a large cosmological constant. That was an argument that Steve Weinberg tried to make pretty accurate by showing that the formation of galaxies is quite sensitive to the value of the cosmological constant, and if it was like 10 or 100 times larger, there'd be a lot fewer galaxies. And so what Joe and I did was sort of to solve the two problems around this at the time rather vague idea, I think. One is to have your theory give you lots of different values that the cosmological constant could take in principle, and the other was to make sure that those are somehow populated and that the universe can find a way to reach all these different values without first getting completely empty. That there's a sort of general problem if you try to sort of reach a small value of the cosmological constant in a targeted way rather than just by accident. You first have to empty out the universe, because only gravity knows what the value of the cosmological constant is. Nothing else measures absolute values of energy in the world. And gravity is distracted by all the other stuff that's around. So that doesn't work. So you have to just make everything. And so we pointed out that the string theory has all the ingredients. It has a lot of extra dimensions, traditionally regarded as maybe a bit of an embarrassment. You have to say, oh, well, they're all curled up. There's like 6 or 7 extra dimensions that are curled up so as to explain why we haven't seen them. And then there's so many possibilities how they could be curled up. I don't know. It doesn't look like a very unique theory anymore. And we kind of just leaned into that and said, yeah, exactly. It's not unique at this effective low energy regime at which we find ourselves. Just like the standard model can make 100 different elements, and out of those elements you can make uncountably different combinations of like molecules and how you could arrange them, right? Just think of protein folding, and to say nothing of the macroscopic world. The numbers are, unimaginably large of just combinatorics you get, the possible things you could do. Maybe the way that our world came from string theory works the same way. That and we did some combinatorics. We showed that the kind of ingredients that Joe had recently discovered, D-branes, can be arranged in different ways in these extra dimensions. They give rise to something called fluxes, somewhat analogous to electric fields. And you can estimate how many different ways can you go down from the 10-dimensional sort of fundamental description of string theory, which would still be quite unique, to making stuff. Making, for example, a 3+1 dimensional world with curled up dimensions. And we found the numbers are enormous. It could easily be 10 to the 500. Estimates vary. The point isn't exactly how much. The point is, you're thinking of the vacuum that we see around us as not a particularly profound, deep, fundamental thing, but like one arrangement of some fundamental ingredients, and there could have been many other arrangements. And we argued in particular that the spectrum or the possible values of this cosmological constant that is so remarkably small where we live, indeed can be very fine. But because of the way that these vacua are arranged in string theory, you can find a vacuum like ours without first emptying out the universe. You don't have to go step by step by step by step to smaller values of the cosmological constant as you had to in some early models that tried to realize Weinberg's idea. You get to sort of move around in a multidimensional landscape where most likely our parent vacuum actually had an enormous cosmological constant. The arrangement is pretty random. And so you can come down with a lot of energy to spare, and you can make the Big Bang, as we usually think about it, would just be the decay of our parent vacuum into ours, and there's enough energy to go around to heat the universe up and give you a hot Big Bang and actually make the model consistent. That was really the big obstruction, making the model consistent with standard cosmology.
Yeah, well, before I derailed you, you were explaining how the multiverse, when connected with many worlds, could help account for the probabilities of quantum mechanics. And this is another, for philosophers, many of the philosophers I've spoken to, including Sean Carroll, philosopher and physicist, probabilities are one of those sore spots that they're still grappling with, and why they're very interested in discussing the quote-unquote interpretations of quantum mechanics. Yeah. So I'm curious about the connection here.
I think that's fair, by the way. I mean, I've been using sore spots. Yeah, exactly. I think I was using sore spots as like, I think you should be able to tolerate a little more pain than that. It's the examples I gave are like, yeah, that makes you uncomfortable, but that doesn't mean it's wrong. But I agree, if Sean, for example, presumably has pointed out that we don't know how to derive the so-called Born rule from quantum mechanics itself, it feels like it would be cool if that wasn't just an axiom of the theory and we could derive it from the others. I don't know. I don't have a particularly strong opinion on how serious of a problem I think this is. It's always nice to make the axiomatic foundation of a theory leaner, right? If there's something you can derive from the other axioms, shouldn't be in there, but that doesn't necessarily make it a bad thing. At some point, it's going to stop, and some things are just fundamental, and you have to accept them. I don't know. Anyway, so I agree that is a very interesting question. One of the questions that I think have a real validity that we should examine about quantum mechanics. But what Lenny and I were worried about, it was a little bit different maybe. We were worried about the fact that if quantum mechanics is indeed fundamental and is going to survive at the most fundamental level of a description of nature, which we don't know for sure, but let's just assume for the purposes of this argument that it's true, then what are the observables? What are the precise things that we can hope to compute from it? And as we've sort of touched on many times without really saying it out loud, probabilities are very important to how we use quantum mechanics, how we use it to describe the world, how we use it to describe experiments. And when you talk about probabilities, you are, strictly speaking, talking about a concept which becomes rigorous and exact only if you can repeat an experiment infinitely many times. Right? Because when I say that there's a 60% chance that it's going to rain tomorrow, well, people sometimes laugh when especially when the weather report says there's a 50% chance, and people will say, oh no, that's like these idiots, they're just telling us they have no idea if it's going to rain tomorrow or not. Well, it's a little better than that, right? What they're saying is, in situations like the one we're in today, with the knowledge we have, half of the time it ends up raining and half of the time it doesn't. Okay, that's that's not that you know nothing. It's that, unfortunately, it's impossible to predict exactly what's going to happen, and it's particularly uncertain right now. But when you think about it that way, like just over the years, if you look at the weather forecast, and indeed it turns out that 50%, every time they predicted 50% chance of rain, you check what happened the next day, and you average it, and you say, oh yeah, it's true. 50% of the time it rained, 50% of the time didn't, and you say, okay, you know what? Maybe these people actually kind of know what they're talking about. What would be bad if it turned out that 80% of the time it rained and 20% the sun was shining? Because then they could have given us a better prediction, right? And they were not doing as well as they possibly could. So that's an example where we see that to make sense of probabilities, and in particular to decide whether someone's theory, in this case the weather services theory, is a good theory or not when it's a probabilistic theory, is we've got to repeat the experiment many times so that we can compare the data, ratios of times that something actually happened versus the other thing, to the prediction. And that becomes exact, strictly speaking, only when we repeat it an infinite number of times, because hey, there could have been some crazy fluctuation. If I just look at 10 such days, maybe they just got unlucky. It's true, yeah, the sun was shining every single time, but turns out that if I looked at a sample of 100, now all of a sudden it's almost equal sun and rain. So, it was a fluke. Right? So to really be sure that the 100 still isn't a fluke, well, maybe look at 1,000. So, to be 100% sure that you're doing everything with no uncertainty left, you need infinitely many repetitions. And now back to our paper, in cosmology, that's really hard to do. We're in a part of the universe where even if we were not limited by our own mortality, or by the fact that the sun is going to run out of fuel, or many other catastrophes that will probably be more relevant in the short term, we would be slowly decaying and cooked to death by some sort of weak radiation over the eons, as the universe empties out and is still accelerating, and there turns out to be a little bit of a kind of Hawking-like radiation that permeates it. It's not an environment where you can live forever. Even with the best of protection and intentions, if you go out in your best spacesuit and you've made yourself, some kind of, machine that lives forever, no, you can't. There's laws of physics that tell you that you're going to decay. You're going to run out of energy. You're going to run out of free energy, to be precise, and you get absorbed into randomness, and so we can't, in particular, repeat experiments infinitely many times. And so, this is not one of our most pressing practical considerations. But as physicists, it is often, when you're a theorist, it's often useful to ask whether the quantities that you're calculating have rigorous operational meaning. And clearly, probabilities coming out of quantum mechanics in the situation that we find ourselves in do not. Right? Not at the absolutely infinitely precise level. Like in practice, of course, we don't care about, repeating an experiment infinitely many times. We just do it enough to rule out the theory with like a very high degree of confidence, and then we move on and try to find a different theory. But yeah, so this is a very sort of maybe abstract or abstruse point of view, but it's often valuable to ask, well, could you really make this completely precise? And the answer is no. And so we looked for places where you can maybe make it precise, and we found such places. We're not likely to be the lucky observers who get there, but there are places where the vacuum energy density, or the cosmological constant, is exactly zero. At least in the string landscape, there should be such places, because in the string landscape, there are places where a certain symmetry that can make it be exactly zero is not broken, unlike in the part of the universe where we find ourselves in. It's called supersymmetry. So there are places where, the vacuum energy is zero, and if you make it there, you can live there forever. And moreover, you get access to an infinite amount of matter over time, like an unbounded amount of matter. No matter how much you want to see, how much you want to look at, how much you want to experiment, it's going to be given to you. And so we argued that, while we may not be the lucky ones that get to make precise sense of quantum mechanical amplitudes, and we really never cared, right? We've gone through life without ever repeating an experiment infinitely many times. That as a matter of principle, it is interesting that there might exist such regions, and that the string theory landscape naturally contains them, in which an observer that is born there or somehow makes it into them is able to perform experiments infinitely many times and perhaps get arbitrarily good statistics and test quantum mechanical amplitudes to arbitrary precision.
Okay, well, since Sean just came up a couple of minutes ago and we have been toying with some quantum gravity territory just a little bit, I wanted to ask one thing that might, again, motivate discussions of the interpretations of quantum mechanics. And I think this might have been my last conversation with Sean. He said that he thinks that the way, or at least one of the most plausible ways to make progress on quantum gravity is to go back to the foundations of quantum mechanics and to get clearer on issues like the measurement problem or many worlds or spontaneous collapse theories. He didn't actually give those examples, but they're just coming to my mind now. And I'm wondering if this then is not the way that you would go about continuing to work on quantum gravity, which is something clearly that you're doing. So,
I'll try to give you a nuanced answer to this question. So I don't think, personally, that by wildly speculating about modifications of quantum mechanics, look, first of all, let 1,000 flowers bloom. We all do better as a community by having different people have different intuitions, different career paths, different feelings about what should happen, how it should work. That's how we explore, and that's great. But for me personally, I don't. Doesn't smell right to me. That doesn't smell right to me. It's too arbitrary, and it's too strongly, for me, founded on an irrational discomfort with quantum mechanics as it presents itself to us. And so I don't think that it has the right markers, the right pointers built into it. I think you're moving away from the truth. But I've given you an example where, by being sloppy about quantum mechanics and the emergence of classical phenomena, we may have gotten ourselves into a lot of trouble. And that's when I talked about the multiverse or any universe in which you have what is called eternal inflation. You have this sort of eternal self-reproduction. It just grows and grows and grows, and different stuff happens in different places. I was complaining that when we describe this kind of thing, we pretend to have definite outcomes happen in different places, when in fact we should be using the spider's description. Remember the spider that has surrounded the galaxy? Everything is happening simultaneously. It's all one big coherent state. And I think that by being careful about that and not making this mistake, we can at least prevent ourselves from, we can do many things. First of all, we'll prevent ourselves from going down a completely wrong road, talking about spacetimes that have just no justification in terms of even arising in a semi-classical limit. It just doesn't make sense. But we can also ask, what does this actually tell us about the regime of validity of our current description of space and time? How confident can we be that we understand this as well as we do? So about 5 years ago, there were some developments in the study of quantum gravity, specifically black holes, that really reinforced my determination to take these things as seriously as I've just advocated we should take them. That development was when we discovered, more precisely, largely through the work of some of my colleagues here, Jeff Pennington and Luca Iliesiu, and a number of other young people, they discovered that this sort of a little bit primitive seeming mix of Einstein's theory of gravity, general relativity, on the one hand, which is classical theory, and quantum field theory, quantum mechanics, that we've been using to describe the world so far, is secretly much better and much more powerful than you might think. Not to say that it's the final answer or anything like that. It's not the quantum theory of gravity. But if you follow the rules, and in particular respect the fact that when you're talking about the whole universe, you can't say that there are observers that happen to not see this or that environment. You've got to just evolve your whole quantum state like the spider would for the galaxy. If you follow those rules, you get extremely powerful results from the theory. In particular, Jeff was able to show that this relatively primitive framework allows you to predict that black holes return quantum information, something that we thought we needed, string theory, very advanced concepts for. If you just ask gravity nicely, it'll tell you that. And it's absolutely critical in that analysis that you don't introduce an environment, that you evolve the quantum state without ever forgetting about any part of the information as it sort of makes its way forward in time in the world. And so I think there is, at that level, there is some interplay between the kind of questions that we grapple with, like how does classicality emerge? Oh, it emerges by forgetting about some part of the quantum state. And our attempts to understand quantum gravity, do black holes return information? Well, in that analysis, we better not forget about part. So I don't have anything to say that's going to really close this loop, but I wanted to point at places where I think there is some contact. Like that work about the quantum properties of black holes has certainly reinforced my confidence that we were right in insisting that a quantum description of the whole universe can involve like randomly forgetting about part of the information and then saying, oh, here's my universe, and here's a bubble of new vacuum that forms here and there. It's not a consistent description. It would sort of break a lot of the progress that we've made elsewhere in physics, in addition to never having made much sense to me in the first place.
Well, Raphael, we've had two conversations in this very room now. I have so thoroughly enjoyed both of them. I'm looking forward now to a third, maybe, where we will get to go over some of these thoughts and questions I have about holography that we didn't get to today. But thank you again so much for talking about QM with me today.
Thank you.